We now begin our investigation of the last type of function we're dealing with in this course, and that is the concept of a vector field. A vector field combines the idea of multivariate function and vector valued function. It is a multivariate vector valued function. That is, it takes a vector, it takes more than one variable as an input, and gives you a vector, gives you multiple variables as an output. Most of what we'll be dealing with are vector fields in the plane. That is, they take x and y and they give you a vector, in a two-dimensional vector on the end, or functions that take three variables and give you a vector in 3 space. Now you can envision a vector field, at least in 2 dimensions. We can sketch one. Imagine fluid flowing through a pipe. So you'd expect that, especially the more viscous the fluid is, the closer a point we take to the walls of the pipe, you would imagine, due to friction, that there'd be a relatively small, relatively low velocity near the walls. Although near the center, you'd expect maybe the velocity to be a little higher. So this gives us, at any point, it gives us vectors that indicate the velocity of the fluid flow. Near the sides, the velocity is going to be small. Near the middle, the velocity we expect to be greater in magnitude. So where there are 3 main operations we want to look at for vector fields. The first isn't something that we apply to a vector field. It is a way to construct a vector field, and that we've actually seen already, and that's the gradient. So given any multivariate function f, if we take its gradient, this gives us the vector of partial derivatives. And this is a vector-valued multivariate function. So this is a vector field. Given any multivariate function f, its gradient is a vector field. So this is a field, is a vector field. And the original function f is called its potential function. We'll see more examples down the line of potential functions. These turn out to be very important in what we're going to study subsequently. We'll look at ways that you can find potential functions and determine if a vector field actually has a potential, because not everyone does. The next operation we'll look at is called the curl of a vector field, and this is denoted as this del symbol cross f. And this is the curl of f. And what this tells us, in some sense, at a given point, how much twist there is in a vector field. So if we were to take this example up here of fluid flowing through a pipe, at these points where the pipe is straight, you would expect there to be not any real bend in the vector field. Things are flowing along smoothly down the pipe. But if, say, there was a bend, then over here you'd expect there to be a little twist in the way the fluid is flowing. So this twist right here tells us we have some curl in the vector field. In the 2D case, curl is sometimes called the rotation of f, although I will not use this notation here. If you see it later on in your studies, you'll know what it means, that it means just the curl. And the last one we look at is the so-called divergence, where we take this del symbol and dot it with their vector field f. This is called the divergence of f, or sometimes noted as div f. And the divergence gives us an idea of where the sinks and the sources in a vector field are. So if we have the same situation where we have, say, fluid flowing down a pipe. Now this may not happen in the real world physically for this specific example, although hopefully this illustrates what divergence means. Say at a given point we may have much more fluid flowing into that point than we do flowing out of it. So here we've got a lot of extra fluid flowing in versus fluid flowing out. So this tells us that somehow there's got to be a sink here. There's got to be a fluid sink. So here the divergence would be negative, and that tells us we have a sink. And likewise, if at some point later down the pipe, at this point not much fluid is flowing in but a lot of fluid is flowing out, here the divergence is positive, and this is a source. Since there's more fluid flowing out than flowing in, there must be fluid being created at this point. And if we're in a situation where the divergence is 0, then that point is neither a source nor a sink. In many physical vector fields, the divergence is 0 everywhere due to conservation of matter. So let's actually look at an example of each of these. Now, divergence, Gradient we've seen a lot of in the past. Let's just summarize with another example of gradient. So we take the gradient of this function, say x y squared z cubed, and this gives us a vector whose components are the partial derivatives. So this gives us y squared z cubed for our x component. Then the partial with respect to y is 2x y z cubed, and the partial with respect to z is 3x y squared z squared. So this is a vector field, and this function is its potential. So this is constructing a vector field using the gradient. Our next operation is the curl. So let's do a specific example. Let's say we got the curl of xy, and then x squared plus z squared, and then 2xyz. So now the curl is a cross product, which means we've got to set this up as a determinant. We're going to take the determinant of a certain 3x3 matrix. The top row in the determinant, because it's a cross product, will be I, j, and k. The second row are the three entries in this vector. Now this isn't really a vector, this is just helpful notation to remember the formula for curl. And this is the partial derivative operators, the partial with respect to x, the partial with respect to y, and the partial with respect to z. And then the bottom row of our determinant will be the three entries in the vector field. So xy, x squared plus z squared, and 2xyz. Let's go through and take this curl. So this will be I times, well, now we're going to cover everything in the same row and column as the I. That leaves us with this 2 by 2. Now to evaluate this 2 by 2, we're going to do that cross multiply trick. We're not really multiplying though. This is saying apply the partial derivative with respect to y to this entry. So when we sort of think of cross multiplying here, it's the partial with respect to y of 2xyz minus the partial with respect to z of x squared plus z squared. So let's go through and do those two partials. So the partial with respect to y of this corner entry is 2xz minus the partial with respect to z of this middle entry here is 2z. So that was the I entry. Now we're going to look at the negative j. And the j, we do the same thing. We cover everything in the same row or column as the j. And if we look at what's left over, we've got this 2 by 2. And again, this means apply the partial with respect to x of 2xyz minus the partial with respect to z of xy. So this gives us 2yz minus 0. And now we go to the k component of our curl. So again, we cover everything in the same row or column as the k. And that leaves us with this 2 by 2. So here we're going to take the partial with respect to x of x squared plus z squared minus the partial with respect to y of xy. So we throw those two partials in there and we get 2x minus x. So that gives us, for the curl of our vector field, another vector field. And so this gives us 2xz minus 2z, comma negative 2yz, and then x. So this is the vector field we get by taking the curl. So note that the gradient takes a multivariate function and gives us a field. The curl takes a field and gives us a field. And then finally the divergence, because this is a dot product, will take a field and turn it back into a multivariate function again. So let's do an example of the curl. So let's say we've got x squared plus y squared, and then 2xyz, and then our last one will be, say, y squared minus e to the x plus z. So now to evaluate this is a dot product. So think of this like this gradient symbol right here is the three partial derivatives, the partial with respect to x, partial with respect to y, partial with respect to z. And we're dotting it with this function right here, x squared plus y squared, 2xyz, y squared minus e to the x plus z. That means we'll multiply the first two entries together. Now this is not really multiplication. Think of it as applying the partial with respect to x to the first component. So that gives us 2x. And then we apply the partial with respect to y to the second component. That's 2xz. And apply the partial with respect to z to the third component, which gives us 1. So this is the divergence of this vector field. Oh, I just said it wasn't a vector. And this is a dot product, so we add these three together. So this gives us 2x plus 2xz plus 1 as the divergence of our vector field. So the divergence takes a vector field and gives us a multivariate function. So with that in mind, let's see what happens if we actually compound these together. We know that the gradient takes a function and gives us a field. We know the curl takes a field, gives us a field. And we know that the divergence takes a field and gives us a function. So there are certain results that I encourage you to check. The first is that if I take the curl of the gradient of f, so the gradient turns a function into a field, the curl takes that field, turns it into another field, this actually is always 0. Okay. And if we compose these two together, if I take the curl of a field and then take its divergence, this is also going to be 0, although this is the 0 scalar because we've done the divergence